Alright folks, today we're going to teach you how to do the 20s Winnie the Pooh. There's some mathematics that are involved and they won't make a lot of sense until we get a little bit further into the unit, but this is one of the key concepts for this unit. Winnie the Pooh would also be the content that will be on one part of your test, which will be next week. The reason this topic, this unit is so important, equilibrium and what we call the Chatelier's principle is so important, is it's one of the main topics that are used if you go out into industry and you are to make a product using your chemistry skills. This particular unit will come in very handy. So if we look at this very first part right here that we have, some of the information that it gives us on the top of your sheet is that we have products over reactants. We're also going to use the coefficients that come with each of the products and the reactants, and we're going to make them be to a certain power. So that's where those coefficients come in. So we put products over reactants, we put brackets around it. The brackets mean molarity. So anytime you see this, that means molarity. That's from our last unit. And if we remember from the lab that we just did yesterday, solids and liquids won't show up in our K equations. So the only thing that will show up in our K equations will be aqueous and gases, and coefficients become powers. So let's do a few problems and make sure you understand what is going on. So in this particular problem, we have a K that is quite large. If K is actually over 1, we are going to say that the reaction is going to go to mostly products. That would mean it's a big arrow going that way and a small arrow going this way. This is what we experienced with our strong acids and bases. They broke apart completely. So, again, if you have a K over 1, it means we're going to get a lot of products out of that particular reaction. In this next instance, we have a K that's small. And if K is less than 1, it means that it's not going to go over the product side. And actually, you're going to have many of your reactants left over. And we could symbolize that with a big arrow going towards the reactant. So if we would look at the concentrations, we would find a lot of reactants in the container and not a lot of products in the container. This would be like our weak acids and bases from our last unit. And if the K is exactly 1, it means that both reactions are occurring at the same rate. That means the reactants are forming the products at the same rate that the products are forming back into reactants. And that's when a K is exactly 1. We won't do this demonstration because, well, you just can't see it. So we're going to go to number 1 on your sheet. And it's asking us to write the equilibrium expression that we have here. So again, K is going to be equal to the products, the molarities of the products, over the molarity of the reactants. We're not going to include solids or liquids. So K is going to be equal to NO. We put molarity brackets around it, and we bring down its coefficient to the second power. And then we're going to multiply that by our next reactant, or excuse me, our next product, which is H3AsO4. And we're going to bring down its coefficient as a power, so to the third. And we're not going to include water because water is a liquid and its molarity simply won't change. So solids and liquids, their molarities don't change, and therefore they do not enter our K equations. Put my line. Now I'm going to go get my reactants. So I'll start with this one right here. H3A H2SO3. That's going to go to the power of 3. And it doesn't matter which order these go in. You could have the H3ASO3 go first, or you could have HNO3 go first. So this is going to be HNO3, and its coefficient is a 2, so that means it goes to the power of 2. Next, you're going to put in numbers for all of those items. So 1B is putting in all of the numbers. So K is going to equal, and our NO is this value, so that's going to be 0.81 to the second times, then we're going to do this part right here. So that is 0.79, and that's going to go to the power of 3. Put my line. We'll do this part next. So that is going to be 0.23, and that is going to be to the third power. And then the very last part that we have to do is the HNO3, which is this part. And that one is 0.55, and that's going to go to the second. Take a second, crunch all that into your calculator, and then come back to me and we'll check and see if your answer is correct. Hopefully you did take a chance and punch that into your calculator, because calculator mistakes are the biggest errors that we have in this unit. If you crunch this into your calculator, you should get 87.89. Sig fig wise though, since we have 2 sigs for all of our numbers, the answer would be 88. This would mean this number is greater than 1, which would mean this particular reaction would favor the making of products. So we should end up with a lot more products available than reactants. At any point in time, pause the playing of this and watch what's going on. In number 2, we're going to write the K equation. So K is going to be products over reactants. This guy right here is a solid, not going to be included. This guy right here is a solid, not going to be included. So we would simply have Fe, 2 positive, no exponent. And then on the bottom we'd have Ag, positive. And the exponent for that would be 2. So that would be our equilibrium expression. If you wanted to, you could bring this down and you could go a 1 if you wanted to, and down here go a 1 if you wanted to, but it would not be necessary. Why don't you see if you can do the next part all by yourself? And then play the video and see if you are correct. Well, hopefully you did pause the video and try this one yourself, because I'd really like you to do that. But here we go. So in this problem, this one is a solid, not going to be included. This one's a liquid, not going to be included. So our K equation in this problem would be Al2SO4, 3, and there's no exponent. And SO2, coefficient's a 3, so that means my exponent's a 3. On the other side, we have just H2SO4. And our coefficient's a 6, so that means our exponent is going to be a 6. Put the numbers in, crunch it on your calculator, and see how you do. So pause the program and do a little bit of work, and then come back to me. Hopefully you did pause the program. So for aluminum sulfate, that concentration is 1.01, and there's no exponent up there to worry about. And SO2, sulfur dioxide, that is 2.19. And if we look, it goes to the third power. On the bottom, H2SO4 is 1.23. and its exponent is a 6. So please pause the program and see if you can crunch that number yourself, and then we'll check it up here. Well, hopefully pause the program. This is 3.06. That's your K value. That means this reaction would favor the products over the reactants. The backside is your homework. Come in for questions if you have any questions.